My name is Amira, and now I'll be explaining about the definition of addressing mode. An addressing mode refers to the way the CPU identifies the location of data or operand that is needed for an instruction. In other words, it tells the processor where to find the data, whether the data is in a register, in memory, or given directly in the instruction itself. Using different addressing modes gives flexibility to programmers and allows more efficient data manipulation during program execution. Next, addressing modes in the Motorola 68000 processor. Now let's look at the addressing modes used in the Motorola 68000 processor. First, data register direct. This mode uses a data register as the operand. For example, the syntax is DN, such as DO or D1. Here, the operand is stored directly inside the data register. Second, address register direct. In this mode, the operand is stored in an address register. The syntax is AN, like AO or A1. It is usually used to hold memory addresses instead of data values. Immediate addressing. Third, immediate addressing. In immediate addressing, the operand is given directly in the instruction. The syntax uses a hash symbol, for example, hashtag 5. This means the value 5 is part of the instruction itself and not stored anywhere else. Fourth, absolute addressing. In this mode, the operand is located at a specific memory address. The syntax can be a label or $address. This means the instruction will directly access data from a fixed memory location. Next, we're moving on to the number 5, indirect addressing. In this group, the operand is not in the register itself, but in the memory location pointed to by the register. Let's go through each type briefly. A. Addressing register indirect. The syntax is AN. This means the operand is stored in the memory location whose address is in the address register AN. B. Address register indirect with post increment. The syntax is AN plus. Here the operand is accessed first and then the register AN is automatically incremented. This is commonly used when accessing consecutive data like in arrays. C. Addressing registers indirect with pre-decrement. The syntax is negative AN. In this case, AN is decremented first before the operand is accessed. It's often used when processing data in reverse order such as stacks. D. Address register indirect with displacement. The syntax is DAN. This means the operand is at the address AN plus some offset or displacement value. E. Address register indirect with index and displacement. The syntax is DAN XN size. Here, the operand address is calculated by combining the register AN, a displacement, and an index register. It's useful for accessing elements in arrays or structures. 6. Counter relative. This mode uses the program counter as the base address. The syntax is DPC or DPCXN size. It means the operand's location is relative to the current instruction. This mode is commonly used in branch or jump instructions. 7. Immediate addressing. Lastly, we have immediate addressing with syntax hashtag data. The operand value is written directly inside the instruction. For example, move hashtag 5 DO means the value 5 is moved directly into register DO. Okay, move on to the code section. On the right, we can see an example of assembly code written in the Easy68K simulator. It includes move, add, and sub instructions to demonstrate different addressing modes in action.
Hi, I'm Nurul Azlin. Moving on to the next question. Give examples of a M68000 assembly program that performs additions of two numbers using at least three addressing modes. The first program begins at memory address $1000, which is set by the origin directive. The first instructions, move immediate 5 to data register D0, loads the number 5 into the first data register called D0. Next, move immediate 10 to data register D1, loads the number 10 into the second data register D1. Then, add D1 to D0 means the computer adds the value in D1 to the value in D0. So now D0 will contain the result of 5 plus 10, which equals to 50. The next line, move D0 to memory address $2000, store this result, 15 into the memory location and address 2000. Now, for the second part of the program, move immediate 3 to D2, loads the number 3 into data register D2, then load effective address $2000 to address register A0, puts the memory address 2000 into the address register name A0. Finally, add D2 to the contents of A0 means we add the value stored in D2, which is 3, to the value stored at the memory locations pointed to by A0. In other words, to the value in memory address 2000. Since memory address 2000 already contains 15, after these instructions becomes 15 plus 3, which equals to 18. The last instruction, sim_halt, ends the simulation. In summary, the first program performs addition twice. First between two data register and then between a data register and a memory location. Next, moving on to the next question, give examples of M68000 assembly program that perform subtractions of two numbers using at least three addressing modes. This program demonstrates subtractions operations and shows how the post-increment addressing mode works. First, move immediate 20 to D0 loads the value 20 into data register D0. Then, move immediate 5 to D1 loads the value 5 into the data register D1. Next, subtract D1 from D0, perform 20 minus 5, leaving 15 in D0. Then move D0 to memory address $3000, stores the result, 15, into the memory location and address 3000. The second part begins with move immediate 2 to D2, which loads the number 2 into data register D2. Then load effective address $3000 to address register A1, puts the memory address 3000 into address register A1. Now, the instruction subtract D2 from the contents of A1 with post increment performs subtractions using what's called the post increment addressing mode. That means it subtracts the value in D2, which is 2, from the value stored at the address pointed to by A1, which is 15 at address 3000. So 15 minus 2 equals to 13, and that 13 is stored back into memory address 3000. After that, the address in A1 automatically increases by 1. Finally, sim_halt ends the program. So the second program shows how subtraction works and how post-increment addressing automatically updates both the data and the address register.
And now, I will describe every step of the assembly language of Figure 1 using Easy68K simulated. 1. The program starts at memory address 200 using the org command. 2. The instruction move.w hashtag 4ab7d1 loads the hexadecimal value For A, B7 into data register D1. 3. The Note.w D1 instruction inverts all the bits in the D1 bitwise not operation. 4. The instruction move.w hashtag $5E92 D3 loads the value 5E92 into register D3. 5. Or .w D2 D3 performs a bitwise or between register D2 and D3 and the result is stored in D3. 6. Add .w D2 D3 adds the values in D2 and D3 and stores the result in D3. 7. Sub.w D2 D3 subtract the value in D2 from D3 and stores the result in D3. 8. The program ends with the end instruction.
Hi, I'm Danisha Fahana. Moving on to the next question. List all logical and arithmetic instructions in M68K assembly language. These instructions are important because they allow the processor to perform both logical operations and mathematical calculation on data. First is logical instruction. Let's start with logical instruction. This instruction perform bitwise operation or manipulate data logically. First is AND. It performs a bitwise AND between two operands. Second is OR. It performs a bitwise OR operation. Third is EOR, also known as exclusive OR or XOR. It outputs only one when the bits are different. Fourth is NOT. Perform a bitwise NOT, which inverts all the bits of the operand. And fifth is CLR. It clears the operand, setting it to 0. Sixth is TST, tests an operand by updating condition codes but does not store a result. Seventh is ND, ORI, and EORI. These are the immediate version of the logical operation, meaning the operation is done with a constant value directly given in the instruction. For example, the instruction ANDI hashtag 5 DO performs a bitwise and between register DO and the value 5. Second is arithmetic instruction. Next, we have arithmetic instruction which perform mathematical operations such as addition, subtraction, multiplication, and division. First is add, adds two operands. Second is ADDI, it adds an immediate value. Third is ADDQ, it adds quick, used for adding a small constant. Fourth is sub, SUBI, and SUBQ, perform subtraction, with SUBI and SUBQ being the immediate and quick version. Fifth is negates a number using two complement form, and sixth is CMP, compares two values and updates condition codes without storing the result. Seventh is CMPI, it compare immediate value, and eighth is MULS and MULU, multiply signed and unsigned values respectively. Ninth is DIVS and DIVU, it divides signed and unsigned values. Moving on to question 2. Convert the expression below into an assembly language instruction. To begin, we need to convert all numbers into hexadecimal for easier handling in assembly language. First, 1011111 is in binary is BF16. Next, DADA is already in hexadecimal. Finally, 1234 in octal is equal to 29C16 in hexadecimal. Now, the expression becomes BF times DADA plus 29C. To write this in assembly language, we typically break it down using common instruction. Here's one way. MOV AX BF, move the value BF into register AX. Second is MUL DADA, multiply AX with DADA. And third is add AX 29C, add 29C to the result. So the final assembly instruction are MOV AX BF, MUL DADA, ADDAX 29C. And that completes the conversion. Moving on to the Motorola 68K assembly program that performs basic arithmetic using register and instruction. The program starts at address $3000. It loads two values into register, multiplies them, adds a constant, and then stops. So ORG $3000 sets the start address. Move.L hashtag $BF DO loads $BF into DO. Move.L hashtag $DADA D1 loads $DADA into D1. MULU D1 DO multiplies DO by D1. Add.L hashtag $29C DO adds $29C to DO. Sim halt stops the program so we can see the result. The final result is stored in DO. This program shows data movement, arithmetic, and program control in 68K assembly. In short, this simple program shows how assembly can perform real calculation.